Hi everyone. So see this example. Let's say we have a power n, b power n such that n is greater than equal to 1. What it means, I want the same number of a's before b's and then same number of b's after a. Okay. So what will be the let's suppose we want to draw the finite automata for it. Okay. So first of all, what we have to do, find out the language. So the if we put n equal to 1, what will happen? It becomes ab. Then if we put n equal to 2, it becomes a b b a b and so on. So these are the strings present in the language. So let's try to accept this language with the help of FA. FA means with the help of DFA or NFA. Let's try to draw it. So let's suppose we have state. So minimum, see, language is infinite. So then minimum string is AB. So draw the skeleton for it. A, B, I'll accept it. Okay. Now fill all the transitions. So let me give naming A, B, C. Okay. For A we have a transition. Yeah, one more thing. Sigma here is A comma B. Okay. On is capital A state, I have a transition for a small a. If small b comes, what should I do? See, it should only come with a, start with a and end with b. Actually, you might think like this. So what should we do? If b occurs in the starting, because in starting what we want only a's to come, right? So in starting, if b comes, I'll create a new state, or that state will come. Okay. Now check here at state B, if A comes, still A's are before B, so I don't have problem. So at B, if B comes, yeah, don't have the problem. Okay, now if A comes here, I cannot accept it because after B, A cannot come according to this language. So I go to the where that state. So you might think this is the DFA for this language, but see what is the problem here is it is able to count one A here and one B here, but check example, check the string A if I give this string to this FA, what happens? A and then B, it will accept it, but in the language we don't have this, because in the language what it is saying, if the number of A are 2, then B should also 2. Okay, here number of A's are 2 and number of B's are only 1. So what should I do? Are you analyzing what is the problem which is coming? See, I scan whole string from this FA, but somehow this FA is not able to store the count of more than 1A. Are you getting? See, 1A comes, it is storing it. It knows that 1A is already arrived. But after 1A, how many number of A's can come? It cannot store it. It can pass from this FA, but it is not able to store the number of A's count. Okay, same is here problem. See, 1b can come here. It can store also that 1b has come, but after 1b the number of b's count will not be storing here in C. So this is the problem in the finite automata. So what to do? so to so what we want finite automata plus infinite memory. Okay, so that it should able to count the number of A's and check for number of B's also that they are equal or not. Therefore we can say that this language is not accepted by what finite automata. Okay, so we want finite automata plus infinite memory, and this comes under PDA, that is called as the push down automata. Okay, we'll see it later. So here what I wanted to show you that there are certain languages also possible that they cannot be accepted by the finite automata. That is why we need some other automatas. Okay, so that is why let's check the family of languages, or what are all the automatas possible. So see, and one more thing I want to clear it, that those language which are accepted by the finite automata, see, language accepted by finite automata, either FA or NFA, called as the regular language. Okay, see, this language is not accepted by the finite automata, so it is not a regular language, it is something else. We'll see it later, don't worry about it. So there are certain languages, and corresponding automata is also present there to accept that language. So let's see what are all languages. so so first one is the regular language. Okay, wait. Regular language. Okay, and if you want to check the example, that is a power n such that n is greater than equal to 1. Okay, then we have mm, context free language. Okay, then we have context sensitive language. After it we have recursive enumerable sets. So this is all is called as the family of language. Okay, for CFL, if you want to see example, I'll tell you a power n b power n such that n is greater than equal to 1. Okay, for CSL we can have example a power n b power n c power n such that n is greater than equal to 1. Okay, and for RE sets, let's see a power p such that p is prime number. Okay, these are the languages which are present overall. Regular language, then we have context free language, then we have context sensitive language, and then we have recursively enumerable sets. Okay, and this is one example I have shown to you. See, for each of the language there is a corresponding automata to accept it. And we have studied the FA. For Wrangler language, we have finite automata. For CFL, we have what? PDA, push down automata. Okay, we'll go one by one to every automatas, but let for CSL we have linearly bounded automata. Okay, now for recursively enumerable languages or sets, we have Turing machine. Okay, now there is something called as the grammar also present for each of the language. See, with the help of that grammar we can generate the language. Okay, so for regular grammar we have, for regular language we have a regular grammar. For CFL we have context free grammar, CFG. For CSL we have context sensitive grammar, and then for recursively enabled sets we have unrestricted grammar. Okay, so this is all called as the family of languages. These are all languages possible, and corresponding it has all the automatas which can be accepting the particular language, and then these language can be generated by the by these grammars. Okay, thank you.